and welcome again to Chemcracker. Today we're going to look at the pH of weak acids. Okay, now weak acids are different from strong acids in that they are only slightly dissociated, but different acids have different degrees of dissociation. So what we have to do to calculate the pH of weak acids is that we must first of all get the concentration of the H plus concentration, but to do that we cannot just infer the H plus concentration from the equation because we have to know the degree of dissociation. Now, the degree of dissociation can be represented in a couple of ways. One, we can use the acid dissociation constant, or we can use percentage dissociation. I'm going to show you both ways using two examples. Now, example one, we're going to use the Ka value to calculate the pH of a weak acid. Now, this example says, what is the pH of 0.01 molar methanoic acid solution? And you're given Ka of methanoic acid. So the first thing I'm going to go ahead and do is that I'm going to write the equation for dissociation of methanoic acid. Now, methanoic acid could be written HCO2H or HCOOH. It doesn't matter which way you write it, as long as you have it correct. So that is my equation for dissociation. Now remember, this is not a one-to-one dissociation in terms of what actually happens in the aqueous solution. Okay, it is a one-to-one according to the equation, but when it dissolves in aqueous solution, only a small proportion actually dissociates. Now, so we can write Ka for this to be equal to H plus concentration times the methanoic ion concentration over HCOOH concentration. And if we assume that HCOO minus concentration is equal to H plus concentration, we can rewrite that to say now we ultimately want to calculate the pH. So that means that we have to get the H plus concentration. So if I make H plus concentration the subject here, I'm going to bring this over here. So it's going to be the product of Ka times concentration of HCOOH. Okay? And because this is squared, I would have to square root this side. Okay? Therefore, H plus concentration here, if we just fit in the values here, will be the square root of Ka, which is 1.8 times 10 to the minus 4 times the concentration, which is 0.01. Now, that is going to be equal to the square root of 1.8 times 10 to the minus 6. And if you do that on your calculator, you are going to get 1.34 times 10 to the minus 3 mole per dm cubed. Now the pH is going to be equal to minus log 1.34 times 10 to the minus 3, because pH is minus log H plus concentration. And that will give you 2.87. Now, in our second example, you're asked to calculate the pH of 1 molar HA that is 1% dissociated. And of course, if it's only 1% dissociated, that means it's a weak acid. So let's look at it. Now, since we have HA as the formula, we can write the equation for dissociation as H plus A minus. H equals to H plus A minus. Now, we're told that there is a 1% dissociation. Now, this is a 1 mole to 1 mole ratio in terms of the equation. We're told that when you go across that line, in real life, there's only 1% that dissociates. And that means that although I start with a 1 molar concentration here, the H plus ions formed from that will be 1% of what is over here. So this is going to be 1 over 100 times 1, which is 0.01 mole per dm cubed. And so we've got our concentration of H plus ions there. So H plus concentration is going to be 0.01 mole per dm cube. So therefore we can get the pH because pH is minus log H plus, and that turns out to be very simple, minus log 0.01, which is going to be 2.00. Pause.
One.
Thank you again for joining us on Chemcracker. Please share the video, make a comment, like, and subscribe for more Chemcracker.